Welcome to my quick 5-minute Python tutorial on k-nearest neighbors for multi-class classification on the iris dataset. As I just said, we'll be using the iris dataset, a typical introductory dataset that is already clean and ready to go. In this tutorial, I'll try to give a good understanding of how many data science topics relate so that you can start to dig deeper on your own using Python. To save time, I'm going to assume that you already have Python downloaded, as well as packages like NumPy and Pandas. To begin, load the iris dataset after you've loaded your libraries. After that is loaded, we're then going to look at the scatterplot matrix. So if we look here at the scatterplot matrix, we can see that a lot of the variables like sepal length, sepal width, petal length, etc. are linearly separable, which will play nicely with k-nearest neighbors. So in the case of a multi-class classification, we need to use the classification method that can handle more than a binary response, hence why we're using KNN. So in this case, we're going to be measuring the relative distance between k number of points and matching closer ones together, hence the name k-nearest neighbors. In the process of selecting a model like KNN, you must first consider a few things. One, how many independent variables do you have relative to the size of your dataset? Because this is a small dataset, it is good that we only have a few parameters. This is also the reason why we aren't using something like a neural network, which often requires a large amount of data. A model like KNN suffers greatly from the curse of dimensionality. I'm sure you've heard about that before. For example, in image classification, there can be thousands of parameters or millions of parameters depending on the data set. A model like KNN would not perform well on this type of data set because it relies on the relative Euclidean distances between points. Second, KNN works very well when there's a strong linear separation between factors within a given variable, which is the case in the iris dataset. So now, moving on, now that we've looked at that, we can go ahead and encode our variables. Because our dependent variable is a categorical variable, we're going to have to encode it. Fortunately, because we loaded it through scikit-learn, it's already encoded, but just make sure that the KNN algorithm applies it as such. We'll go through and run this. After that, we have to split our data set into a training set and a test set. In this case, we'll use 80% for the training and 20% for the test set. Right now, we won't do a validation set primarily because of the size of the data set and because there isn't a ton of variability within the species category. If it were the case that certain variables weren't linearly separable, it would be of greater importance to also tune our model to a validation set to eliminate possible bias in the model. Next, we will scale our features. This is important because if, let's say we're talking about predicting someone's job title through salary and age. Salary is a much larger number than age. So in Euclidean distance and Euclidean space, it's going to play much more greatly than the age factor. Now we are ready to train our classification model. In this case, we will select k equal to 5 or 10, well specifically 5 for this case, but 5 to 10 is generally sufficient for any problem without too much overfitting using KNN. If you want to do this more scientifically, you can implement a grid search or Bayesian search on large data sets that may require better performance, which is a technique that is often used to find the best hyperparameter settings, but we won't do that here. So after that, we can look at the confusion matrix. As you can see, we pretty much got 100% accuracy on this. What you want to see is zeros everywhere but the diagonal. Finally, to ensure that we're not actually just getting 100% because of some random selection bias, we're going to use k-fold cross-validation. In this case, we'll do 5 folds. So what will happen, we'll first train on splits 1 through 4 and test on 5. We'll then train on 1 through 3 and 5 and then test on 4, so on and so forth. After doing that, if we go here and look at the accuracies, we can see that it's likely we got 100% because of selection bias, but we still did pretty well on the other cross-validations, averaging somewhere around 92%, with a standard deviation of about 3%.